So ever since my channel started doing decent a couple of years ago, I've dreamed of building some sort of decoration for my desk to remind me of all of you guys. All 98,195 of you. So I guess this also comes with my interest of sort of branching out into electronics. So I like doing embedded programming, networking, that kind of stuff you see in my channel. But I also like making electronic things. I know I'm not very good at woodworking, but I thought at least circuit boards would be something I could tackle. So I built this whole beauty around Nixie tubes. So in the 1960s especially, this was a very popular form of display tube. It's a cold gas tube with 10 digits in it. So by making the angry pixies flow in the right way, you can light up each of the 10 digits directly. So you can have these display a number. By having a grid of them, you can display, well, a lot of numbers. Now Nixie tubes, of course, fell out of favor in the West. They got displaced by vacuum fluorescent displays and light-emitting diodes, which are much easier to work with electronically. But I like the glow and the charm of the Nixie tubes, and I thought it'd be a fun project. So I learned that they were actually still produced all the way through the end of the Soviet Union over there. So I bought a set of 12 of them from Ukraine. So a couple of months ago, I attempted this project using a desktop CNC mill. And while they did a pretty nice job with the wood housing, this is one of my scraps, by the way, it was much harder to do circuit boards on the mill. Now I know a lot of people do mill circuit boards, and it's something that does work, but I learned that my design skills were not that great, and even in the 60s when the Nixie tubes were popular, they would have been using better methods back then. So thanks to the help of PCBWay, I was able to build my dream subscriber counter using relatively modern electronics that I designed. So if you're interested in how I design the electronics, how I manufacture this whole thing, and how AI led me astray on this project, then come along in this adventure. So before I start though, what even is a Nixie tube? So most of you guys think tube, you probably think of something like this. It's a picture I found on the internet. It's a vacuum tube. So these were diodes, triodes, other sort of current control devices. They rely on a heated cathode, which spews out electrons, a grid, maybe multiple grids to control the flow of electrons, stuff like that. We also have more specialist vacuum tubes like the klystron radio tube, which was used in all kinds of cool stuff, and the really sci-fi looking mercury arc rectifier. Another form of vacuum tube is the cathode ray tube. So works similarly. We have a heated cathode, it spits out electrons. We accelerate and steer those electrons with electromagnetic fields until they hit a phosphor and then light up. That's how we make a picture on a TV. Before the transistor was invented, by the way. Nixie tubes don't work that way. They don't have a heated cathode. We just have a whole bunch of cathodes stacked up. We don't have a control grid, we just have an anode. And they essentially just glow because of the gas in the tubes. They're a gas-filled tube. And they're filled with a mixture of neon and argon, so they're much more similar to like a neon lamp or neon indicator than an actual vacuum tube. So driving them is fairly simple. We have 10 digits, so we have 10 cathodes, we have one anode. We just have to apply a voltage between the anode and the cathode, and we need about 180 volts or so to get the tube to light. Once it lights, it will draw a lot more current. We need to reduce that current, so we use a current limiting resistor. Not that complicated. What does get a little bit complicated is I have 6 tubes. That means I have 60 cathodes and 6 anodes. I could just hook all the anodes up together to 180 volts. That's nice and easy. On the low side though, I have to deal with 60 little cathode drivers. These could be like NPN transistors, which would be a hell of a lot of transistors. If I did that then, I would probably not have enough pins on any microcontroller I could choose. And I want to solder this thing by hand, so like high pin count micros aren't really an option. My next option is to select the high sides, so if I put transistors on each of the 6 high sides, I can then select one of the tubes, pick the appropriate cathode for that tube. Now I'm down from 60 into my 6 high side selects, and my 10 cathodes, which is 16 pins. That's not bad, and I probably could have taken that approach if I wanted. Downside now is that each tube is only on for 1/6 of the time because I'm scanning them. And so that means that now I only have 1/6 the brightness. Now the tubes are relatively bright as is. They can be scanned like this and they do look very nice. I decided I wanted a bit more brightness, so I split them into 2 halves. So I have 3 high sides and 20 low sides. And because integrated circuits were invented in the 1960s, we have an integrated circuit that does just this. The 7441 or 74141, these were designed directly to drive Nixie tubes. So we take 4 inputs that tells us in binary the number we want to display. For the extra 6 digits, it just turns the tube off, which is nice and convenient. And they turn on the correct low side and drive the tube. Now unfortunately, the 7441 and 141 have been out of production for decades, But for some strange reason, apparently the Soviet Union continued producing them in Belarus all the way through the 2000s. So I don't know what the Belarusians were doing, but I bought some of their Soviet clone chips, the KD something something. I don't really know Cyrillic, so I don't know the exact translation, but I got 12 of those to drive my low sides. So that brings my total pin count to 11. I have 2 low side drives, each of one needs 4 bits. I got 3 high side drives, plus I need the high voltage driver to generate 180 volts. So with all that said, I guess it's time to take it apart and show you the electronics that I've actually built. So these are just held in with hot glue because I am a terrible craftsman. Okay, got the brass off. Now I got 4 globs of hot glue down in there. That I hope are not as hard as the other ones were. So I got it apart. Here's the enclosure, by the way. This was almost entirely done on the mill. I pocketed much more of it this time for this enclosure. Made it a little bit less deep too. Didn't spend as much time on the finishing pass. The idea is that this sits down on the bottom. So it sits, I guess, up a little bit on the desk. And there's a hole in the back for the power wire. And for the actual board itself, I guess it goes this way. So here are the Nixies. I'm still using the milled board that actually holds the tubes. And I got a brand new PCB made for me by PCBWay for the electronics, with its very own ESP32 on it for Wi-Fi. I'll very carefully pull this off. So here's the power board. Maybe I'll overlay a few schematics as I go through this. Basically, this side has the 10 cathodes for the first 3 tubes, and this side has the 10 cathodes for the other 3. Here are the 2 Soviet ICs here that are driving the cathodes. I've got 3 copies of the anode drive circuit up here. It's got a PNP and an NPN transistor. So I need to pull the PNP down to apply 180 volts to the tube. That's done with an NPN that pulls down the base of the PNP, so I can safely isolate the microcontroller and some resistors in there for protection. This whole thing in the center here is my high voltage boost converter. So to generate 180 volts, I basically have an inductor. I connect it to ground through a transistor, which is this guy right here, I believe, is one of these 2, is the high voltage transistor. And this guy, when he switches, he pulls it to ground. We build up a current in the inductor, which is right here. As the current builds up, we then switch off the transistor, and it dumps that energy stored in the electromagnetic field here through a diode into these 2 high voltage capacitors. Now I actually did have to do a bodge here. I got a little bit of a story on that. So you can probably see my extra transistor here. So for the high voltage drive, I'm driving it with a MOSFET. I really wanted to use one of these smaller package MOSFETs in like a TO220, which is like this size, because this was really big and I wasn't sure it was going to fit on the board. So I found a MOSFET that worked, and it should have met all the specs. I then needed to drive that MOSFET, and in order to drive the MOSFET, this is one of the big problems I had with my last design. So I do a lot of stuff in the digital world. I don't deal with analog circuitry like this that often. So I very naively copied someone's schematic, and I thought it was an Arduino-based project. Now Arduino would run at 5 volts, which is higher than the 3.3 volts of my ESP32C3, but I didn't recognize that problem, and I thought it would probably work, and it didn't. And so I couldn't get the transistor to switch, and so I looked at it and I was like, well, maybe I needed 5 volts. So I got out a real Arduino, hooked it up, and it still didn't work. Then I looked at what they were actually doing, and they were actually driving with a 555 timer at 10 volts, which is a little bit different from an Arduino at 5 volts and very different from an ESP32 at 3.3 volts. So essentially, I'm not even reaching the threshold voltage of the MOSFET at 3.3. I need at least about 5 for that. And even the threshold voltage, I'm not conducting very well. I really need to turn it on at about 10 volts. And so I have 12 volts. That's what my power supply is. So I have a voltage available. If I can get the MOSFET gate up to 12 volts, it'll turn on nicely. So I need an amplifier. And so I looked around. The most common amplifier you see is made with a BJT pair. So an NPN and a PNP. It's called a totem pole amplifier. It's also essentially a Class B amplifier circuit, or Class AB, I guess. So I was going to use that. But then I realized there's another problem. In order to drive the circuit, I need 12 volts also. So that drives high current into and out of the gate of the FET, but I still need a 12 volt booster for that. So then I bring in another NPN and a pull-up resistor. But now I've inverted it, so now every time the microcontroller reboots, we turn on the MOSFET and then short out the inductor, which is bad. So I thought I would ask an AI for a solution to this. I went to Claude, pasted in my schematic, and asked for advice, and he gave me this. And I guess, pushed back and thought that this seems a bit wrong. I mean, not being an electrical engineer, it seemed wrong to me to have the NPN on the top and the PNP on the bottom, because I'm so used to PNPs being high-side transistors and NPNs being low-side transistors. So the fact that he had put those back where I thought they should be made some sense to me, but it didn't match a lot of the examples online, but it matched some of them. So I kind of went with it and I built the circuit anyway. And Claude, of course, was dead wrong. The NPN needs to go on top, the PNP needs to go on the bottom, and I must have one more NPN transistor to invert. So because I'm inverting with my amplifier with a pull-up resistor, I need another one to uninvert it so that when the whole system powers up, I don't turn the MOSFET on. So you may be able to tell here that I kept changing out resistor, trying to make the circuit work. I kept trying to drive more current through the different MOSFETs in different ways, or different BJTs, and I just couldn't come up with anything that made that circuit design work. So eventually I pulled out some of these resistors. I added another gate resistor here, as you can probably see. I doubled that one up. And so I ended up with a NPN on top, a PNP on bottom, a driving transistor that's an NPN, and then another one to invert it again. So this is the inversion stage here. So I'm coming in from the micro, going into this NPN. That's pulled up by 12 volts from this bodge wire. That's grounded by ground from this bodge wire, etc. So that's one of two bodges I had to make. The other one relates to Wi-Fi. So I'm using the ESP32C3 for Wi-Fi because it seemed like a good choice, I guess. And I didn't realize that the power requirements when Wi-Fi is transmitting are really, really high. So I was looking at how much power this consumes and being like, I need like 150 milliamps or so on the 3.3 volt-ish. Seems good. I mean, it's only powering the ESP32, nothing else. The logic chips are 5 volt powered, and I have a pretty beefy 5 volt regulator for that. So I wasn't too worried about the 5 volt, and then I had the 5 volt reg driving a 3.3 volt reg, so I don't have too much heat in the tiny little 3.3 volt reg here, which can do 150 milliamps. And I thought, great. But while the average power might be 150 milliamps, the peak power when actually transmitting on a Wi-Fi could be as high as 700. And so I had a big cap here, and I thought that would be enough, and that was nowhere near enough. So the problem I ended up having was that the regulator can do 150 milliamps from a 12 volt supply, but not from a 5 volt supply. The dropout is too poor. So I bodged it in to power it off the 12 volt directly and then cut one of the 5 volt traces to it. So now the regulator input is 12 volts and the dropout is such that it can handle more current, and that was enough to survive the Wi-Fi pulsing. And I do still have a really big capacitor on it. I guess you can see my bodge up here close. So I got the brown bodge wire goes over to this capacitor, which is the input filter cap to the regulator. Then I have another output filter cap and then a bulk capacitor here, which I guess is 270. And then I have another bulk capacitor on the 5 volt over here. And the 5 volt mostly powers these ICs and some of the other gate drive stuff. And then I've also got a feedback resistor that's like a 200 to 1 or something, 100 to 1, that brings down the high voltage into an analog input on the ESP. I sample that. The ESP is pulsing away to generate the high voltage, and it works remarkably well. This is still the tube board I made in the last episode. It's actually completed now with all 6 tubes, and I had a couple changes here as well that I did in place. The biggest change is this thing doesn't have solder masks, so when you actually go to solder these little pads, it really sucks, and you get a lot of mistakes. So I had to spend a lot of time, especially in this corner over here, cleaning up mistakes, trying to get it to solder cleanly, and I'm also soldering pins up, which is the wrong direction. So this was a huge pain, and this pin over here just broke as I pulled it apart, so that kind of sucks. I think I may make another tube board in the future, but probably not make a whole video about it. So yeah, I just uploaded my Gerbers from KiCad, ordered it. It only took a few days to ship. It took like a day or so to make them. I picked relatively easy board material, so this is just basic FR4 two-sided copper, which is like the most common. You can also get them in different colors, which is cool, but I wanted them fast, so I got them in green, which is like the quick color, I guess. And so here are my fully populated boards. They, of course, sent me 5 because that's sort of the minimum quantity, but I just populated one. I don't actually have enough parts to build all 5 of these, but that's okay. So I thought you guys might be interested in the Nixie driving code a bit too. So I got 2 files here I'm going to show, Nixie.c and highvolt.c. So here I start off with some definitions. So I have 3 high side switches and 2 low side groups. So I have to define all the pin numbers of what maps to what. Because I didn't do a one-to-one mapping between the Soviet drivers and the tubes because it was easier to route, I have to remap all these digits here. So you can see this is what, if you want to drive a 0, you need to actually drive a 2, and if you want to drive a 1, you need to drive an 8, that sort of stuff. And they're different for the 2 low sides, of course. And then to drive a single digit, you pick a high side, a low side, and a digit. So this would be like high side 0, 1, 2, low side 0, 1, and then digit would be 0 through 9. and then it calculates what bits have to get turned on and off of that low side, and if the high side needs to turn on at all, because we don't turn on the high side if the digit isn't on at all. And so then in the periodic task, we just take the global variable Nixie display, which is written to by the HTTP code in main, and then we convert it into 6 digits by recursively dividing by 10, basically. And then we go back from the beginning and we set all leading digits to 0 and turn them off, so we don't have to display leading zeros. And then we can either drive them sequentially, where we drive half and then half. So this is literally driving 6 tubes one at a time. Or we can do 2 at a time with this set of code down here, and I'm playing around with which one I like better. There's a little bit of ghosting if you have multiple tubes on at the same time and one of them isn't driven. So the leading zeros can sometimes ghost a little bit if I turn them off. And then we just use the FreeRTOS task delay. I've set it up for a 1 kilohertz timer, so these are in milliseconds. So this time is a couple of milliseconds, basically. So we end up with about a 50 hertz scan rate. Over on the high voltage code, I started with some examples from the analog to digital converter example. So I'm setting up the AD converter. This is all just example code, basically. And then I'm using a module called the RMT, which is designed to do infrared remote transmitter and receiver. And this gave me the option to do a variable on time, variable off time. Most of the PWM generators, you set a duty cycle and you set a frequency, or you set the total cycle time. And I wanted to vary the total cycle time but keep the on time the same. So I literally just turn it on and off. So I have an on time and an off time. And I leave the on time constant the whole time. It's 17. This is in 2 megahertz, so it would be about 8 microseconds or so. And then I vary the off time to have more pulses to do more energy transfer. I just kind of used an oscilloscope to measure that waveform and see what looked relatively efficient for the inductor, so I figured that out at 17. So down here I just read the A to D 10 times and I add them all up. This converts it to millivolts, but I already have a 100 to 1 divider, so this would be volts times 10 at the high voltage rail. But then because I'm adding 10 of them, I end up with volts times 100, so I have 185.00 to get 185 volts. So I do a little bit of a integral controller here. We limit ourselves to the max min off time, and we update the transmitter to do more or less pulses. And well, I guess that's all I got today for this project. I really enjoyed working on this, even though some bits of it were a huge pain, like working with 60-year-old technology. I guess always is. I definitely have some electronics projects I'd like to continue doing in the future. I guess more close to what I normally do now, networking related, that kind of stuff. This did really tickle my itch a bit, though, to do more embedded electronics. So, like, my career has always been in embedded electronics, not sort of main computer stuff. So, working with low-level programming on the ESP, which isn't even that low-level, was quite fun for me. So maybe I'll do some more low-level related stuff. I guess comment if you have any projects you think would be neat for me to do there. One project that I thought of while I was working on this is a friend of mine while I was working on this in the Hack Lab actually had an engine control ECU that was about 20 years old that died in a car. And I thought, you know, I could just make one of those, because about 10 years ago I was this close to actually making my own engine ECU. But back then it was harder to get circuit boards made quickly. The lead times were worse. It wasn't as easy to order parts and stuff like that than it is now. Now it should be significantly easier of a task, hardware-wise at least, and there's software examples available and stuff. Of course, internal combustion's in decline, but I did enjoy working on that back when I used to work on engines long ago. That's what I did embedded programming for, by the way, was engines. So real-time fuel, spark, airflow calculations, that kind of stuff. Torque. So maybe I'll jump into car stuff in the future, I don't know. Maybe I'll just stick to stuff like this. Fiber optic transceivers, that sort of circuitry. But feel free to comment down below if you have anything you want to talk about. Also, big thanks to PCBWay for making this project possible. Go ahead and check them out if you have any circuit board or other rapid prototype manufacturing needs. If you want to do any more lengthy conversation with me, Discord, link down below for that. I also sell merch. This is not one of my shirts, this is a Jeff Geerling shirt, but most of the shirts that I make, they're available on my website, or actually on my Ko-fi. Link down below for that as well. And I guess I'll see you guys on the next adventure.